All right, I've got a fun one for us this time. We're going to learn about two very powerful concepts. The first is called SIMD, that's how you pronounce it, or how most people tend to pronounce it. And then we'll learn about how floating point operations can be done in assembly. So that is, I know, something you've been waiting for. So let's start off with a concept called Flynn's taxonomy. It's a 2x2 grid. It's just this little square, but it's a powerful square with a lot of meaning. All right, it's going to classify the ways that our processors could be potentially executing instructions. We prefer different corners of this square for different purposes. Okay, so it's named after like Flynn is the person's last name. It's named after a dude from Stanford who came up with this back in the 60s, and it has stood the test of time, just kind of like Moore's law, right? So there are two axes to this that builds this 4x4 box. There's an instruction stream axis and a data stream axis, and you can either have single instructions or multiple instructions, or single data or multiple data. All right, what in the world does that mean? Think of a stream kind of like file streams in C++. You've got like a bunch of things coming. It's like a river of things. So a stream is just like a flow of data or a flow of instructions. Like, here are all the instructions that I would like to eventually execute. Like, I got an add instruction. I've got a sub instruction that I want to do after that. I've got a mul instruction. You can think of your programs as like a stream of instructions, right, that you want to have executed. And there's plenty more after that, where that came from. So that's one axis. And then you have a stream of data that you'd like to act on, right? Maybe you're getting a bunch of data from a sensor, like you're getting readings from like a heart monitor or something. Like, you're getting a bunch of ints, let's say 42, 43, 1, 2, 0, and maybe it never stops. All right, so you've got a stream of data that you want to act on. Maybe you want to sum up the values, compute a rolling average, something like that. And so you can make computers that deal with like multiple instructions at once, that deal with single instructions at once, that deal with single pieces of data at once, that deal with multiple pieces of data at once. All right, and that's where this four corners concept comes in. That's where the taxonomy comes in. You've got let's say you got SISD, SIMD, MISD, and MIMD, I guess. Who knows? Pronounce it however you'd like. But at least this one, people tend to say SIMD. All right, so SISD, I guess, that stands for single instruction, single data. Okay, that's what that means. And you can build a processor that works like that, right? It's executing a single stream of instructions. All right, so like a single program, and those instructions are working on single units of data. Okay, which makes a lot of sense, doesn't it? So that's what we essentially think of when we think of a CPU. We're imagining most of our processors like this, right? That's very logical. What else could we possibly want? Except for like that concept about forking and threads, we've pretty much, in your computer science career, been talking about SISD processors, okay? And they were pretty much all like this up until the mid-2000s, okay? So yeah, that's all that we know how to do. Like, we're executing single bunches of instructions one at a time, and they're operating on single units of data, like add these registers into this other register. And that's just like how a program should be, right? And so this is kind of how we've been taught so far, and that's all we know. But there's other concepts, all right? There's more axes than just this, right? Maybe instead of running a single add instruction, add R0, R1, R2, we could bring it down into like MISD, right? Single data, single instructions, multiple data, right? We could go into SIMD land, which is like, all right, in addition to adding R1 and R2 into R0, please also, in that same add instruction, add R4 and R5 into R3, okay? And by R, I mean like W or something. Sorry, I'm thinking about the last time I taught this class, and we were doing 32-bit ARM stuff. So here, let me rewrite all that. Forget I said R. Something like, all right, add W1 and W2 into W0, and then also at the same time as that, add W4 and W5 into W3. Wouldn't that be cool? Like, you do both at once? Like, it's multiple data, right? But it's just one single instruction acting on multiple pieces of data, doing the same thing, though. Wouldn't it be nice if you can do that a lot of times? That's SIMD. Okay, does that make sense? So instead of just one instruction, operating on single chunks of data, like you have other axes, and let's explain those other options. All right. So another one could be MISD. All right. Multiple instruction streams, a single piece of data though. That's the idea. Single data stream. So this is when multiple instructions, single data. That's what it stands for. If you're on this corner of the square, this taxonomy, then you have multiple instruction streams working on a single data stream. All right. And this is hard to wrap your mind around, I know, but a good reason that you might want to do this, have multiple instruction streams acting on the same data, is like maybe you have two versions of the same program. Like you make a blue version of the program, and you make a green version of the program. Maybe they're slightly different, like one was programmed by one group, one was programmed by a different group. So multiple instruction streams, two things at once, and then they're acting on the same data, like a sensor reading. For like, maybe you're in a plane and this is like altitude or something, or heading. Like you got these values coming at you, one at a time though. 20, 40, 80, I don't know, numbers. And you're feeding these sensor readings into single pieces of data at a time into the blue program and into the green program. So a good example of that is like these two programs are running at once, the same multiple instructions on the same data, so they can check each other's work, so that you know like when there's an error. It's easier to spot errors if you have multiple instructions acting on single data streams. Okay, so a good example would be like just something that's mission critical, like you have flight control programs like in an airplane or for like a space shuttle even. You can imagine that you want to be very fault tolerant there, and you don't want just one bug in one version of code that's going to blow up the space shuttle. So you'd rather, okay, let's write 3 versions of this code that all are acting on the same data, and they can check each other's work, and we can just go by majority rule, and that can control our giant billion-dollar spacecraft. Okay, not very common these days in other areas, but in certain areas like this, that's something that you would do. Okay, you'd make processors that are able to work this kind of way. All right, and then SIMD is the one that people care about the most. That's the one that is very popular. It's this idea. All right, this idea where you're doing the same thing on multiple pieces of data, multiple strings of data, but single instruction streams. All right, so SysD processors, let's see, we're working like that. SIMD processors are running the same instruction, right? Single instruction stream, so one instruction at a time on multiple pieces of data, multiple streams of data simultaneously. All right, and the reason we care so much about SIMD processing is because GPUs are all about SIMD stuff, right? Single instruction, multiple data. They're really good. GPUs are really good at doing the same thing to a bunch of pieces of data. They're really, really good at like messing with a bunch of triangles so that you can draw them really quickly on your screen. Okay, that's what GPUs are good at, right? So yeah, it's just faster if you think about it. Eventually, like get a bunch of 3D coordinates of triangles ready in your giant registers or your memory of your GPU, and then just go act on all of them at once to like calculate the next frame of your video game. It's faster to work on a giant chunk at once. So that's what SIMD is all about. Single instructions, like do an add instruction, please, but have it act on multiple pieces of data, multiple streams of data at once. Like it's kind of like if you could do add W1 and W2 into W0, as well as adding W4 and W5 into W3, as well as adding W6, that's supposed to be a 3, right? As well as adding W7 and W8 into W6, right? Do all these things, do all these additions, shove them there, do these additions, shove them here, and do those all at once. It's parallelized, essentially, okay? So that's single instruction, right? Multiple data, doing the same add to a bunch of things. So that's what GPUs are really good at, and that's why we care, okay? So, yeah. People tend to pronounce this whole idea as SIMD, all right? Like that's what people tend to say, but there's other options, okay? But I'll try to remember to say SIMD. But here's kind of what SIMD is in more picture-esque forms. So like you got a bunch of instructions that you're reading one by one. Like the next one is your add instruction, let's say. You got a bunch of instructions ready to go, and then you feed it out, and you give it to, usually it's called a vector unit. That'll be true for our processor once we learn about SIMD processing in assembly. But you feed that one instruction, and it's like you feed that same instruction to a bunch of different execution pieces. All right, processing units, and then you take from your data pool all of your data. You can take multiple pieces of data at once, feed it in to each one of these individual processing units, which are running the same instruction on all of those data at once. Okay, that's the idea. So another cool example, I like this very blurry image. It's a very useful one though. This is the difference between like your SysD and your SIMD. All right, SysD is all about, all right, we're doing single instructions, like one add instruction, call it a day. Next clock cycle, another separate add instruction. Third clock cycle, a third add instruction. Fourth clock cycle, do a fourth add instruction. So they're all separate instructions working on separate data. Okay. Whereas SIMD is all like this, just like in one clock cycle, do all of this, please. Take like A0 and B0, add it into C0. Take A1 and B1, add it into C1. Take A2, B2, add it into C2, and so on. All right. So do that all at once in one huge chunk, in one huge one clock cycle, essentially. Do all that, please. Okay. So that's what SIMD is all about. All right. And then the final corner, MIMD, I guess, is how you might say it. That stands for multiple instruction, multiple data. And that's when you are working with multiple instruction streams and multiple data streams at once. That's about as flexible as you can get, right? Can't do any better than that. And pretty much every modern day CPU is MIMD because you have a bunch of different cores, right? You have a bunch of different programs, which are their own instruction streams, running and acting on their own pieces of data, which is multiple data streams. All right, so that's pretty much how that works. Modern CPUs these days, they're all MIMD because they're like taken, like you got all your code, you're running that on one core, okay? And that core is talking to memory. You can read from memory all at once, separately, all right? It's like that one is reading from memory here and messing with it and doing stuff, okay? And then you have another core that has its own instruction stream, taking some data from memory over here, has its own data stream. It's able to talk to memory at the same time. And maybe you have 4 cores all doing this. So you got multiple streams of instructions, multiple execution units, all acting on different pieces of data out of your memory, let's say. And they all have their own registers too. So yeah, that's MIMD. That's as generalized as you can get, and that's a modern day CPU for you. All right, so you can see why all these corners are kind of useful, hopefully now. And I'll teach you how to do these kinds of processes. There is SIMD instructions in our ARM 64-bit CPU, and I will show you how to make use of them. Okay. Let me get rid of these drawings right here so you can kind of see the words better at least. So yeah, more on this later. Let's switch gears though and talk about floating point assembly, because you want to know how to do that, right? You have a floating point unit now, and we want to be able to talk to it, all right? So in our CPU, in our ARM CPU, it looks pretty much like this, honestly. You have the normal CPU with all of your registers, all of your normal registers. You have all your normal flags. You got your N, Z, CV flags. You have the ability to do like normal adds, normal like branch on if something was equal, comparisons and stuff. And then you have the floating point unit, which is what we're about to talk about. And it has its own operations. It has its own operations that you can perform, and it has its own registers even. Its own little registers. And there's even a third separate place that has SIMD stuff for you. All right. And we'll talk about that one later, but we're going to zoom in and act on floating point right now. Okay, so it's time for floating point. Let's make it happen. And here is a list of every floating point instruction, by the way. Bam. If you want to go here and stare at it for a while. They all start with F, so that's kind of helpful. So you can floating point compare things, floating point add things, and they are different registers, and we will talk about that, okay? So that's where we're going. Let's figure it out. What are these new registers? They're different places to hold like floating point numbers only inside of the floating point unit. Well, here is kind of what they look like, all right? They're all executed in the floating point unit, all these instructions, and so they have their own registers, and here are their names. You have D0 through D31. Those hold doubles, as you might expect. So floating point numbers stored as doubles go there. And there are also, you get D0 through D31. Here's kind of what they look like, D0 all the way to D31, dot, dot, dot. There's also S registers. Oops, for some reason, I tried to press Control Z and it was unhappy. What's going on here? Oh, weird things are happening right now to my PowerPoint. Let's see. Can I erase this? Odd. So let's see if I can save it, and maybe I'll have to restart my PowerPoint. Sorry about this. You'll just have to watch me squirm. Are you happier now? Okay, so we're back, I think. So D0 through D31. So like here's D0 all the way dot 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 to D31. And I can't do Control Z again. It was taking its sweet time. There, it kind of goes. Okay, I'm scared of PowerPoint now. Oh no. But and then you also have your S registers. S registers are for singles. S for singles, single floats, 32-bit floats. And just like W and X registers, your S registers are the right part of D registers, and actually they're part of, even the D registers are part of a bigger register called V registers. There's really V0 through V31, but we're not going to deal with those right now. Okay? So, onwards and upwards, we're going to use these guys as we execute our instructions. It is also possible to do SIMD stuff. Multiple floating point operations at once, multiple add instructions, or like an add instruction acting on multiple V register or D registers, let's say. That is possible, and I might show that to you later, but we're just going to talk about single floating point instructions acting on single floating point registers right now. All right. So here's some common operations that you might want to do. They all start with Fs. All right. So you can go here and kind of see them, like fadd, for example. Maybe it's my browser that's causing the slowdown. Let's see if I reopen it. But they all start with Fs, like fmove, move a constant into a D register, as you would expect. You can't move everything. Sometimes like you can't like move number sign 3.14159 or something, because this has to be encoded in the 32 bits of the instruction, and so only simple things like this can be there. Okay, I hope that makes a little bit of sense. So there's that one. You could just as easily move into S registers. So same thing, just work on S registers, just like you could do W stuff versus X stuff in normal ARM land. Yeah, they all start with Fs, mostly. Some end with Fs. So that's that. This one is kind of useful. This is going to convert an ARM register, a normal CPU register, into a floating point register. Like take a W into an S, like convert, if it was the number 42, the int, it's always going to be an int. Move it into the floating point unit, and let's make it 42.0. That's kind of cool. All right, so it's another kind of moving operation, going from here to here, and also converting types. So that's cool. If you have something long, like you want your constant for pi or something, you want to read that out of a register that holds the address, you can read that with just a normal load instruction into a D register. And then you got like add, subtract, multiply, divide that work on S and D registers. That's happy. And then you have like absolute value, negation, square root, stuff that you would expect. So definitely look at this page. It's cool. It'll show you the kinds of things that you can do. And I want to give you an example. All right. Well, let's make a program that calculates the distance between 2 points. All right. Let's say that we've got coordinates. They're 2D coordinates. And we have both of them. All right, so let's say we've got like, I don't know, this coordinate and this coordinate, and we want to know the difference between them, the distance between them. So the way that we're going to store them is like we got x1, y1 here, and like x2, y2 here. And just for sake of example, let's be like, this is like 3.5, this is like 2.5, and this one is 1.5 comma, I don't know, negative 4.0, something like that. And yeah, we're going to calculate the distance between these 2 points, and remember the formula for that? It's going to be the square root of the square root of x2 minus x1 squared, and you take the absolute value of that. Technically, you don't need the absolute value because you're squaring, but just this is a good example of using absolute value, so we might as well. So we'll do that plus y2 minus y1 absolute value squared. So that's technically you don't need the absolute value because you're squaring, but it's a good excuse to learn that instruction. Technically, you don't need abs. Abs isn't necessary. Okay, but we're going to use it anyway. All right, so I will have you try some of this. Like, stare at this slide, think of what you might use. We're just going to hard code some values, and then when we want to print out our answer, even though we're going to use S registers here, we're going to use normal floats. When you print something in like the printf function call, I think it always needs a double, so we're going to convert it. We're going to f-convert our S register answer into a D register answer, and then it will be happy magically. Okay, so yeah, let's make this happen. Let's try it, and I will stop and like give you a second to pause the video and try it yourself. So here is let's have a main function at least. Let's copy in last lecture's something. Let's do counting is that one. Let's copy that into a file called dist.s for distance. And so what do I want to do here? I guess I can keep my main function like this. I don't really need any saved registers, so let's do sp minus 16, sp plus 16, other than lr, because I'm going to call like printf and stuff. I think that's good. Now let's move our example coordinates into like these registers. Like we'll put x1 in s0, so that's going to go 3.5. And so I'm going to f-move into s0. F-move into s0, 3.5. That'll be my x1. All right. And then my y1 will be 2.5. And that's going in s1, 2.5. That's y1. And then I'll do the same for s2 and 3, right? That'll be 1.5, negative 4. And this is going to be x2 and y2. Negative 4.0 if we want it to be like that. Or, yeah, that should be fine. So let's see, what else? What else do I want to do? This is obviously not to scale. Maybe this should be like negative 1.0. I think then my drawing would make more sense. Please forgive me. I know that's silly, but we'll say negative 1.0 there. So yeah, we've got those values, and now what we want to do is let's say we want to do this. Let's calculate the distance between these points and put the answer into, let's say, S4. That's where I want the answer to end up. All right, so can you try that? So you know where these values are with f moves. We've got them there. Here are your operations that you can use to make this happen. These ones work as you would expect. See if you can do it. You know how to square something, right? That's pretty much it. So follow this formula. And let me go back to the slide if you want to pause there. And then implement the formula. Give it a second. All right, give it a try. And then once you're back, assuming you're back now, let me show you how I might think about this. So we want to do, first things we got to do is subtract the x's and the y's and take their absolute value. So let's do f sub, right? F sub of like x2 and x1, so s2 minus s0. We can put the answer in, we can put the answer back in s0. We don't need the originals anymore. We'll do that for that one. So that's x2 minus x1. Then we'll do the same for y2 and y1. So into s1 can go s3 and minus s1. All right, and then we'll take the absolute value of both of those, and that's going to be an f-abs, which is, funnily enough, the name of the C library function that does the same thing. f-abs. I would like to take the absolute value of s0 and shove it back into s0. So just like that. Same for s1. So now what do we got in these registers? We've got s0 holds the absolute value of x2 minus x1. And s1 holds the absolute value of y2 minus y1. And then we want to square them. So I'll do fmol, right? Fmol them into each other, into themselves. So fmol, just multiply S0 by itself and put the answer back in S0. Same for S1. Okay? And so now we've got, let's see, can I copy this? Would that make it any easier on myself? Maybe. So now I've got this squared. And then same for the y's in S1. There. So I'm almost there. I'm almost home free, right? Now I need to add them. And then take the square root. So it'll be f_add S, I don't know, answer in S0, let's say. S0 and S1. That's me adding the squared differences. And then finally, I can take the square root with f_sqrt. And I want the answer in S4 apparently, so there. So there's my answer, and that's how you compute it. And now, if I'd like to print out the answer, so let's say I want to print out the answer, I'm going to call printf, and I'm going to use like the %f, I think, is going to be my, my little format string. And when you give that to printf, it expects the first floating point argument in a double register, in a D register. Expects the first floating point argument in D0. So we have the answer in S4, got to put it in D0 and also convert it from S to D. All right, so that's going to involve this fconvert into a D register. So fconvert, CVT for convert, into D0 from S4. And then, let's see what else. Dun, dun, dun. I think that's pretty much it. Is there anything else I want to do? Well, I have to print it, of course, so now I need to like put my format string. Put a format string up in here, and I'll just reuse this one. It'll be %f and then a new line. And then I can BL printf, and it'll take the value here, and we're good to go. Beautiful. So I hope that makes sense. Let's see. What else? Is there anything else I wanted to say about this? I think that's pretty much it for now. Let's see if this compiles and runs. Wow, apparently this is the distance. We'll see. I guess we can check our answer, can't we? We're gonna be like 3.5 minus 1.5. That's like 2 squared, and then it's like 3.5 squared. The square root of that. That looks pretty good to me. Nice. Nice. Yay. So it's working, and I hope that makes sense. Please yell at me if it does not. But that's our first taste of floating point assembly. Yay. Okay, next thing. Let's talk about comparing floating point numbers. All right? There's an fcompare for that. It's like, you do this, and it's going to set those NZCV flags just as usual. It's just fcompare rather than normal compare. And then you can branch as normal. Isn't that cool? That's very useful. So let's have an example of this where maybe you can try it, in fact. Let's check and see if the distance between those points was less than 1.0. And you can print yes if it was and no if it wasn't. Yeah? So we've got our distance right now stored. See if you can compare and with the fcompare and make it work. All right? Then you can branch. I do think we might have an issue with this printf call though, so before you go off, let me just go check one thing. I do believe there might be an issue. I want to go to this picture. Aha. So just like, I should tell you this now, just like your X0 through X18 were scratch registers for the normal general purpose registers, in your floating point registers, D0 through D7, those are scratch registers. Ooh. So, if you want a saved register, it's got to go in like D8 through D15. And if you want this value to be preserved across a call, you better save it on the stack as well. but I'm never going to use a D register ever again in this program, so I can just forget about that, and that will be fine. So if I want this answer, you might need to put, and I think it's probably a good example to do it, like printf will clobber. It has the potential of clobbering D0. So it's a good idea to just save it somewhere else. To save this answer somewhere before we call printf. So let's also do like an f move into D8 from D0. Printf will clobber D0. It has the potential to, at least. It's allowed to. How about we say that? So let's save it away somewhere special in a saved floating point register. So yeah, that's what I wanted to say there. Okay. And then if you're using this, if you keep using these values across function calls, you're going to have to do the same thing on the stack here. But I am never ever touching a floating point register ever again, so I do not care about preserving D8 for this program from what it was before, because what it was before was it was not used before. Okay, I know that. So yeah, now I think you can do this example with the f compare. So what you will do is let's check for comparing against 1.0 and less than or equal to-ness. All right. So using D0, let's like print yes or no if it's stored. If the thing there print yes or no if the value is less than or equal to 1.0. Or honestly, I guess it's using D8 now, isn't it? Sorry, just do that. So let's move f move 1.0, that's what we're comparing against. Now we can f compare D8 to D1. D8 is guaranteed to have our answer in it. And then there it is. And now we can print one or the other. So if it's less than or equal to 1.0, I don't know. I'll do it the normal way for once without the opposite. BLE, it was less than or equal to, and then otherwise, if it wasn't less than or equal to, it must have been strictly greater than. All right. So if it was that one, we'll print it was greater than. Otherwise, we'll print it was less than or equal to. So let's print it was greater than first. So that'll be like a printf, BL printf, and then give a format string, or just give a string that holds the idea that it was greater than. I'll just call it like GT. And I'll do the same for this one. I'll call it LE. And I think that will be that. So, oh wait, no, we don't want to fall through here. So we should make like a done. BAL done in that case. So yeah, that's pretty much our comparison. Oh no, what have I done here? Undefined reference. Oh, I need to actually give these strings. Excuse me. So GT can be, honestly, let's just steal this guy. GT can be this C string that just says, what? If it was greater than, it was no, right? No, it was greater than 1.0. And if it was LE, that means it was yes. It was less than or equal to that 1.0 value. So there is the relevant code. And in theory, it will assemble and link properly. And yeah, this one was definitely greater than 1.0. If I hard code something else for a split second, f move into D8, I don't know, 0.5, just for fun, then it is yes. So cool. This seems to be working. Nice. And so yeah, it's not really too bad, is it? It's just new registers, but the operations that you would expect, though they start with F's now maybe, they're very similar to what you know, which is really good news. Okay. So, yeah, I do want to show you one other thing, right? Let's do GDB, because GDB has the ability to inspect registers. By default, it's not going to show you the floating point registers when you print out all your registers with the info registers thing. So let's do a GCC-G. And let's get into GDB, and we'll stop on, let's do line 30, why not? We'll stop on the comparison line, because we have our values in our registers by then. So I'll say GDB dist, and I did the dash G, so I'll say break dist.s line 30, then I'll run the program. And so now, if you wanted to, you can print your individual D registers. Like there's D8, that's totally possible. You just say PD8 with the $sign though, and it will show me what's there in a couple different ways, which has to do with SIMD stuff later. But it's like, okay, as a floating point number in this D8 register, this is what's holding right now. Okay, and so that is the answer. That's what we have there. And like you can print individual registers, like D1, I put 1.0 in it, and you can see that there. But if you wanted to see all the registers, all the floating point registers at once, you could say, you know that there's an info registers, right? Info registers, or IR for short. I space R for short. And then it'll show you these values of the X registers and some other things, even PC, which is nice. If you want to see all the registers, including the floating point ones, you do info registers all, or I space R space A. So there's extra things. Info registers all. So there's, in addition to my X registers, I have my floating point registers. And so I told you that secretly our D registers are part of V registers. And let's see, V1 holds right now. Dun dun dun. D1 holds 1.0. Can we find that here? Oh goodness. So the D part as an F register, I think, yeah, it's printing it out in a weird way. It's printing it out as a not floating point value, so it's kind of unhelpful, but still is showing them to you. 8, D8, here it is. Looks like that. I don't think, yeah, there's probably not an easy way to interpret that as a floating point number immediately. There's even other registers in this machine, Q registers. Disgusting. Okay, there it is. It actually is going to go to the D registers. Nice. That is helpful for us. But still, it's only going to show it to you in hex. Oh, no, it isn't. There it goes. There. That's useful knowledge. There's our 1.0 in D1. There's our 4.03 in D8. So you just press enter long enough. It'll show you everything. It'll also print the S registers. That's super nice. And there's even H registers in this architecture, B registers. Let's not even worry about those right now. And it'll even print the W's. So yeah, so many things. So probably you should just do this. Print whatever register you actually care about, because that was overkill, right? D0. So that's kind of the idea, but yeah, you can do I space R space A for all that. And yeah, that should do it. I want to leave you with that idea of those V registers all over again, because SIMD is very important. We will learn how to do this together. And so you notice that there is some extra space for these registers. Even the D registers don't fill it all up. There's 128-bit V registers that let us do vector operations. That's why it's V. That's what SIMD is all about. So our floating point instructions, the ones I taught you at least, these are scalar floating point instructions. Just do it on individual registers at once. There are also vector floating point instructions. Those are the SIMD forms. All right. If you'd like to know more about them, here is a page that you can go look at. Here's our SIMD vector instructions. There's like an add instruction, a vector add instruction that works on V registers with some dots and some stuff at the end of it. It's a little weird. I'll show you at least one example though, but here's kind of the idea. If you want to do a bunch of floating point instructions at once, you would read a bunch of them, a bunch of floats, a bunch of doubles, into not D or S registers, into V registers. I'll show you how. So like you can section off a V register to be like, it can hold, if it's 128 bits, it can hold 4 separate 32-bit floats, can't it? You can put 4 separate floats in a V register and do that a few times. And once you do that, I'll show you how later, but after that you can do one of your F blah 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 operations on V registers rather than a D register or an S register. And then you have to use a fancy suffix to tell like how we're splitting things up, because it could have been a bunch of doubles or a bunch of floats. So for example, if you were to get V1 and V2 looking like this with these numbers, and you said F add V1 v2, and you put a dot 4s to show that you're breaking up v1 and v2. Interpret them as holding 4 separate single floating point values, 32-bit floats. And then I'd like you to add up all those chunks and add in their answers into v0, again split up by 4 floats. That'll add 1 and 5 into the 6 here, 2 and 6 into 8 here, 3 and 7 into 10 here, 4 and 8 into 12 there. Does that make sense? That's what it will do. And I will show you more of that, more than you can ever hope, or not hope, more than you could ever want to know next time, I think. But that's as much as I want to tease you with right now. So that there is a way to do multiple floating point operations at once. It's called a vector operation, and that's just how SIMD things are called in our ARM architecture. So yeah, look at that page if you'd like to read ahead and get ahead. But I'll tell you a little bit more, at least for whole numbers, next time. But yeah, that was a lot to talk about. We did it. Pat yourself on the back for getting through it. This is definitely a harder lecture, I would say. A lot of concepts at once. But we made it, and I will see you in the next one, as usual.